invitation. So the central object of study for me are the Witten digraph of Linder equations and their solutions. These equations first written down in the early 90s to define a topological quantum field theory. They appear in quantum integrable systems. They appear in singularity theory. They appear in the theory of integrable systems. So they really are a very interesting set of equations and appear in many different areas of mathematics. So while those are the central objects of study, the theme for this talk is their symmetries. And I mean that in a very loose way to generate new solutions to these equations from old solutions to this these equations. And these symmetries will connect up the various 3 bits in the title, the extend Affine Weyl, the duVal, and the hyperplane arrangements. So luckily for me, I'm talking after Alessandro's talk. So a lot of this appeared during his talk before lunch. So I've got a multiplication. The setup is I have a multiplication of vector fields, which I'm assuming is going to be commutative and associative. And there's an inner product with this, what's called the Frobenius property here. In other words, on each tangent space for a manifold, I've got a Frobenius algebra. And I'm not going to write down the full WDVV equations there, until you get used to them. They look very, very strange and complicated. I'm going to write down a differential geometric definition, from which follows the equations if you write them out in a particular coordinate system. So for me, the central objects here is this what's called a Dubrovin connection or a lax pair. We deform a standard Legendre connection associated to the metric by this lambda times this multiplication x times y. So we want the WDVV equations are the conditions for this deformed connection to have 0 curvature and 0 torsion. So the 0 torsion is very quick to see. If you work out the torsion of this deformed connection, the lambda to the naught term vanishes because I've got the Legendre connection, which is torsion free, and the lambda component of the torsion will vanish because of the commutativity assumed as part of the multiplication. The curvature is far more interesting. The curvature term, again, in the last talk, has 3 components: lambda to the naught, lambda, and lambda squared. The lambda squared term vanishes by commutativity and associativity, which I've assumed. The lambda to the naught term is interesting. That just says that we have that this metric at the beginning is flat. The cross term is probably the most interesting bit, most unusual bit, the lambda term of the curvature of this connection. That basically tells you that the covariant derivative of the multiplication is as symmetric as possible. It has a very nice alternative description in terms of F manifolds. And for us, it means there's going to be a pre-potential, a function F, which satisfies a set of equations. But before that, I want to concentrate on the lambda to the naught term, 0 curvature. Calculation of curvature is algorithmic. However, there's a theorem which is always stated that if you've got a metric with flat curve with 0 curvature, there exists a special coordinate system called flat coordinates in which the metric components are all constants. That's very easy to state, but finding those flat coordinates is not algorithmic. You've got to work extremely hard solving sets of equations, differential equations, to find the flat coordinates if you've got a flat metric. So if somebody gives you a metric and say, is this flat? Simple. You just churn handles, compute everything. I have mathematical programs to do it for me. But finding the flat coordinates is a much harder problem. You've got to solve other sets of equations to do that. So I have said the WDV equations are what you get when you unpack all these zero curvature conditions in the coordinate system where the metric has constant form. And in these flat coordinates for this connection, the multiplication of vector fields just takes this form. So F is this pre-potential, it satisfies the equations of associativity, the WDVV equations. So the central object of study for me are these are how to find solutions F to this to the WDV equations, which gives me this multiplication. So there's going to be two ways to generate new solutions from old solutions. The first one is known as a Legendre transformation, or indeed a generalized Legendre transformation. So I'm going to put into the story an identity vector field, little e, so e times x is x, and I'm going to assume, I'm going to consider some vector field delta, and I'm assuming that the inverse vector field exists. Well, so what do I mean by an inverse vector field? I can multiply vectors together, vector fields together. So the inverse vector field is just the vector field which multiplied by delta gives the identity field. And then let's take the Dubrovin connection and just conjugate this. So on one side, I've got lambda in, on one side, I have lambda, on one side, I've got the inverse vector field, and they've got the vector field here. So we're just conjugating the connection. And then you ask the sort of standard question, when does this conjugated object have the same properties as your original object? Now, if you go back to the definition, one thing to think about is the lambda term, the multiplication term in the Dubrovin connection. Having a vector field is inverse on each side of the multiplication, because of commutative and associativity, they just cancel each other out. So from a differential geometric point of view, the multiplication doesn't change. It's the same multiplication. However, the connection part does change. And in particular, when we conjugate, the notion of what's flat for that conjugated connection will change. And that's the origin of the Legendre transformation. So you've got this deformed connection, you've got its conjugated version. You just work out all the curvature conditions, and this is going to play a central role. This invertible vector field is called a generalized Legendre field if it satisfies this differential equation. Now, if you start counting components, this looks to be overdetermined. X and Y are arbitrary vector fields, so we have more equations than unknowns. But remember, we also have an identity vector field. So if you let Y to be the identity field, you get this system here, which is manifestly same number of equations as unknown, and that implies the first equation. And a vector field is Legendre if it's covariantly constant, if it's the flat vector field. And these were the case which Dubrovin originally studied way back in the early 90s. So with this, if you've got any solution to this equation, covariantly constant or not, you can conjugate the Dubrovin connection. It still has exactly the same properties as your original one. And in particular, it's flat, and hence you can construct a new solution to the WDVV equations from the old one. So that's what I've kind of denoted. That's what I've denoted here, starting with F, our original solution, and via some vector, this generalized Legendre field, we can construct a new solution. And you can go back and forward and compose them one after the other, and can start kind of building up symmetries from original solutions. So I wanted to stress that with all four WDVV equations, not for Frobenius manifolds. Of course, WDVV is a central part of the definition of a Frobenius manifold, but there's extra ingredients as well. I'm not going to write out all the extra ingredients, but the important point of this identity field is that it has to be covariantly constant, and also that there's an Euler field such that the multiplication is sort of invariant on the flows generated by the Euler vector field. And from that, you get a stronger notion, this notion of a Frobenius manifold. And this is basically what we've seen the definition of this already in Alessandro's talk. So in the early 2000s, Boris Dubrovin introduced the notion of almost duality. From your old multiplication, you can construct a new multiplication, which I denote star. And from the old metric with round brackets, you can construct a new bracket with angled brackets. And you then start to relate the properties of those two new objects to the old objects you start with. So it's very easy to see that this new multiplication is commutative and associative. That follows completely trivially from the commutativity and associativity of the original multiplication circ. But this new multiplication has an identity field as well, which is capital E, which is the Euler vector field of the original manifold. So it's swapping the roles, some of the roles around. It's called almost duality because not everything is preserved. So part two of this step is what I've just said. This new multiplication is commutative and associative with identity capital E. But in general, this new unity vector identity field dual multiplication will not be covariantly constant. The Frobenius multiplication is very easy to check as well. But then the important property is that this new metric is flat. And then Dubrovin went on to show that there's a dual pre-potential F star, which satisfies the WDVV equations in the flat coordinates of this new dual multiplication. Now that's easy to prove. This sort of computational. There's an essential part where it says this new metric is flat. Let's write everything in the flat coordinates for that flat metric. And of course, that's very hard to do within a specific example. But the coordinate system exists, and it's quite easy then just to write everything down in this new coordinate system, which you know exists, but for specific examples may be very, very hard to find. So what we've got now then is two ways to calculate new solutions from old solutions. You can start with some F, and then you can take a Legendre transformation, and that gives you a new F. Or you can work out from F, you can work out the almost dual solution. And the next result takes a bit of work to calculate, but it's got a pretty obvious really, is that this diagram commutes. So if you start with your original, say, Frobenius manifold F here, and then take almost duality, you get this new solution F star down here. But from F, if I just take a Legendre field, I can take this new object up here. If it's a Legendre field rather than a generalized Legendre field, this object here is actually a Frobenius manifold, which means I can take this almost dual solution to get this object down here. And this diagram commutes, so it doesn't matter how you end up at the bottom right-hand corner from the top left. One thing to note, though, is that the symmetry which connects the Legendre transformation, which connects the objects on the bottom, is the Legendre field at the original Legendre field, but multiplied, twisted by this Euler vector field. And even if you start with a constant Legendre field at the top, this one at the bottom, in general, won't be covariantly constant. You can track everything back. You can work out what the covariant derivative is of this twisted Legendre field in terms of nabla star, which in turn comes from the original connection for F. And you can work out the conditions for which this twisted Legendre field is actually a Legendre field. For all Cox-2 examples, the standard, the most basic sort of examples of Frobenius manifolds, this twisted Legendre field isn't a Legendre field. It remains a generalized Legendre field. But what makes the rest of the talk quite easy from a sort of computational point of view is that for all the examples from now to the end of the talk, this twisted Legendre field is a Legendre field. And you can trace everything back to the spectrum of the original Frobenius manifold. So I'm going to give you basically lots of examples of this now. I'm going to fill in the four corners of this diagram with some just first of all with some three-dimensional examples, some of which we've met already today. So let's start with this object in the top left. We've seen this solution already today. It was Alessandro's talk. So that defines a Frobenius manifold. And if we take a Legendre transformation of that, we get this free potential given by this formula. Now you may recognize this. I'll say more about what these objects are later on in the talk. From this solution.
Yeah, I have just a quick question. So, sorry.
Yeah,
so delta, what is delta here? Do you have a
delta is the delta in this example is d by du3.
Okay.
So when you do the Legendre transformation, the second you involve second derivatives, so you get the log, you get log u3, and basically t3 is log u3, so u3 is e to the t. Okay. So you can actually, in this case, it's one of the ones you can do by hand and perform the Legendre transformation explicitly. Perhaps you say something about the origin of the name Legendre transformation, which kind of appears first in kind of Dubrovin Springer lecture notes for Frobenius manifolds. The new flat coordinates are functions of the dependent variables of the original Frobenius manifold. So it depends on f and its derivatives. So that's sort of the kind of origin of the word Legendre. So we can also take the almost dual solution. If you do the almost dual solution, you get a solution of this x squared log x term, which I believe Sasha will be talking a lot more about in his talk on Wednesday. But then we can also fill in this bottom corner here and get a somewhat strange, more complicated looking form. The Li3 is what's called the trilogarithm. If you haven't come across a special function, the important thing is the third derivative of the trilogarithm is a trigonometric function. So it's the integral of coth 3 times. So that's what you do if you just take some three-dimensional examples of Frobenius manifolds and start composing either almost duality or taking a Legendre transformation. So all this generalizes. So let's kind of, well, let's give the name first before generalizing. This was this B3 example in Alessandro's talk this morning. The example on the top right is an example of a Frobenius manifold coming from that lives on the extended Affine Weyl orbit space C3 over A2, and the thing in brackets is a certain marked node on the A2 Dinkin diagram. So that's because of the symmetry of A2. I could have put 2 there. The object on the bottom left is what's known as the check system. The object on the bottom right goes by a number of names. Solutions of this type were, to my knowledge, first written down by various Russians, Marshakov and his collaborators. I said the WDVV equations appear all over the place. One of the places that they appear is in Gromov-Witten field theory, and solutions of this type were written down by Marshakov and his collaborators in the context of Gromov-Witten field theory. It also appears as the Gromov-Witten generating function. So f contains the infinite, or the Gromov-Witten invariance of a certain resolution of a duVal singularity C2 over Z3, which is work of Brian and Galampor. And this sort of map between these various objects is something I did with a research student, Andrew Riley, a few years ago. So all this actually generalizes to AN and DN. I'll say a bit more about that later, and I'll give a cleaner description of this object on the bottom right. Annoyingly, parts exist for E6, 7, and 8. That bit, so the top right exists. Dubrovin and Zhang had an example, had construction for C7 over E6, etc. was a Pacific Mark node, and Ryan had this sort of object down here. For the A's and the D's, you can show that these are related by almost duality. For the exceptionals, we have two objects here and here, but we don't quite know yet whether or not they can conjecture at least that these two objects are in fact the same object, if you like. They're the symmetries of each other. So let's look then at this, since this one of the themes of this conference is hyperplane arrangements. Just let's look very briefly at this the check system you get on the bottom left. And remember, this was generated by a solution x z squared log z, or more to the point alpha of z squared log alpha of z. So there's roots, there's various roots, vectors, special vectors in the solution. In the simplest case, the Coxeter case, these are just the Coxeter root vectors. Now, in this case, coming from the extended affine Weyl, we've got it slightly different. So the nice thing about three-dimensional examples, you can draw pictures of R3, and if you extract the roots from the solution and kind of plot them, they look like that. So what's the color coding here? The green vectors are just your standard roots in this case of A2. So that's your child's kaleidoscope of mirrors at 6 degrees apart. And all the green vectors are the normals to those mirrors. The red vectors are an extension into this third dimension. What they are is that you take a weight vector in the plane, look at its via orbit, the weight vector, that the orbit of W1 contains 3 vectors, and then you extend them into this perpendicular direction to get these red vectors. How far you extend them is governed by this K parameter, which comes from the Mark node. So this whole configuration of vectors is highly symmetric. It's in n plus one dimensions. The Coxeter group, AN, acts on it. It'll map red vectors to red vectors, and obviously green vectors to green vectors, but it's not a full Coxeter system, a reflection in one of the, if you try to reflect a green vector in the plane defined by one of the red vectors, it doesn't close up, but it still has a huge amount of symmetry and structures. Something else you can see from this picture, when you do a Legendre transformation, you need a vector field. In other words, you need a direction. And from here, there's an obvious direction, which is the direction perpendicular to the plane of the green roots. And so the Legendre field is precisely the vector field that is normal to the plane containing the AN roots. Now, there are other ways there are other directions you can take Legendre transformations in, and that really is a warm-up for Leo Kaminsky's missionized research student for his poster. So what's going on here? What's behind all these four examples of solutions to Frobenius manifolds? Well, there's a very, very simple construction. These are all given by a Landau-Ginzburg superpotential. And that superpotential is just a rational function. And it's a very simple rational function. We have a pole at infinity, and we have a pole at a finite point, T1. And we can make those arbitrary numbers. In here, they're both 1, but we can make the orders as much as completely arbitrary. Now, there's a crucial, and if you've got a Landau-Ginzburg superpotential, there are very, very compact formulas which give you the third derivatives in the metric in terms of taking various residues at the critical points of various functions. But the crucial part of this construction is this form omega here. That tells you that and the kind of work of Koji-Saito, this notion of a primitive form of primary differential equation, that tells you that this is a flat metric. If you don't put something special in this place, if you just put something arbitrary here, you'll certainly get something symmetric, but that object won't necessarily be flat. So it's an essential ingredient in this construction is this omega here. And in this example here, I'm just taking the primitive form just to the obvious one, dp. So if you work everything out with this simple superpotential, it turns out these coordinates T1 and T2 are flat coordinates on the nose for the metric eta. That's not true in general. And sometimes you've got to work quite hard then to work out what the flat coordinates are in terms of coefficients in your superpotential. But this is a very simple example. So the coefficients turn out to be flat coordinates straight away.
This is the unique primitive form. I guess there is some another primitive form having some poles.
Yeah, there are other choices, and I'll come to that in my next slide. It precisely gives you the Legendre transformations. You know far more about this than I do, but different choices of primary primitive form induce a Legendre transformation. So just linked to the last talk, this is one of the 5 two-dimensional semi-simple Frobenius manifolds which have been classified. But as the question, as Professor Saito just said, there are other choices of primary differential equation. There's other choices of primary differential form, and if you make correct choices, those will induce a Legendre transformation between the result of Frobenius manifolds. So here, this is how you change the primary differential equation. The primary differential, you do it. You do it by this formula here, and that just converts. You find that dp tilde is 1 over p minus t2, so that integrates up to log. You invert, you get exponentials appearing. So if you change your your primitive form, you get a new, or the same, depending on your point of view, Landau-Ginzburg potential, which is the one which, with the correct residue formulas, just gives you the extended Affine Weyl kind of orbit space. And all this generalizes to an arbitrary AN case. You just start having higher powers in front of here, and higher positive powers and negative powers. So, let's kind of wind up. And remember, I was originally given half an hour of talk, so we're finishing early. The extended Affine Weyl orbit space Cn over A n minus 1, with K being the marked point. If you work out almost duality, you get one of these tri-logarithm solutions, which appear in the literature already. These are the Gromov generating formulas for certain resolution of one of the simplest duVal singularity. In the middle as well, in my talk, the title of the talk is From Extended Affine Weyl to duVal Singularities via Hyperplane Arrangements. So in the middle of this, you can also think of an interesting hyperplane arrangement, which lives in Cn, which is invariant under the Coxer group AN minus 1, just in the picture I showed earlier with red and green vectors. But in the middle, we've got this kind of hyperplane arrangements. And remember something I said earlier, from a differential geometric point of view, a Legendre transformation doesn't change the multiplication, it changes the flat structure. So over here, even though this looks really, really complicated and contains lots of very interesting enumerative geometry, in some sense, it's the simplest type of multiplication you could have. One over a sort of, in terms of physics language, the simplest 3-point function is 1 over z, which is a third derivative of z squared log z. So from a differential geometric point of view, the multiplication over here is really, really simple. However, to extract the Gromov-Witten invariance, you've got to write everything in the correct flat coordinates. And that's where they kind of the subtleties come in. Now, a lot of this was kind of tying together things in the literature. Well, there is a kind of a new feature here. Well, the simplest kind of the Zn, the cyclic singularities, the Gromov-Witten invariants depend on 2 parameters. That involves far more algebraic geometry that I'm comfortable in explaining, but the AN case, the Gromov-Witten invariance lies kind of 2-parameter ring. So to get the and for the D's and the E's, they lie in a 1-parameter ring. So in the work of Brian and Golampur, to get a unified construction that works for A, D, and E, effectively in the A case, is that the 2 parameters to be the same. And that kills off a term in the an interesting cubic term in the pre-potential. Now, you might wonder then as well what's happened to the parameters. The N and the K over here relates to this specific values here of these 2 independent variables here. So you need an extension to kind of this work. I've been in correspondence with Jim Bryan over this, but I must confess at this moment he's promised me to send me the details, but I haven't seen them yet. What's next? You could also extend these results. In the original Dubrovin exam paper, they on extended affine Weyl Frobenius manifolds, they do all the Frobenius, all the Weyl algebras for A, and in the construction there's a mark node. There's certain root theoretic data you need, which you can think of as marking a node in the corresponding diagram. For the A case, they showed that you could take that mark node to be any one of the nodes. But in the original construction, for all other Weyl groups, they could only get the construction to work for a specific mark node. A few years ago, Dubrovin and Zhang, myself, and Dafeng Zhu extended the results for the classical cases to an arbitrary mark node, and then you can just do all this construction again and extend everything to binary dihedral duVal singularities. And the essential part is in the superpotential. It's a function not of z, but it's a function of z squared. So you get this extra kind of z2 invariant rational Landau-Ginzburg superpotential. So finally, then, what do we know about to complete the picture? Well, that's complicated. That for E6 and 7, the objects on both sides are known. The original Dubrovin and Zhang construction, albeit for a Pacific mark node, exists as a construction here. There's also the construction of Brian and Golampur over here. So one can conjecture that the 2 are connected by almost duality, and also conjecture that there's an interesting arrangement of hyperplane arrangements in the middle somehow in dimension 7, 8, and 9. But currently, that's not known. I mean, there, as perhaps Caroline might tell us in the talk this afternoon, the spectral curve for these objects is a higher genus curve. So computationally, it's much harder to work everything out. One could almost do almost duality by hand, but that's a massive, if you know all the flat invariants, there's nothing to stop you with a very big computer doing everything. So, I mean, it's a massive computational problem either way. But conjecturally, then, one would complete the picture then and connect all extended affine, all of the resolutions of duVal singularities with certain extended affine Weyl orbit spaces with interesting hyperplane arrangements sitting in the middle. Thank you.